Hello again. Hope you're doing okay. Today we're doing something called quantifiers, which is probably going to be new to most of you, but thankfully it's not a difficult concept. Just weird looking symbols, but they're not hard to understand. And I think today's video is going to be the shortest one we've had so far. So I've probably said this a few times in class. Math likes symbols because we don't want to have to say the same thing, which takes several words, every time we want to communicate the concept. If we can just write a single symbol and get the same point across. So what do we want to get across? Sometimes we like to talk about the characteristics of a group of numbers. Maybe all natural numbers have a certain interesting characteristic and we want to focus on that. Or sometimes we want to focus on characteristics of a single interesting number and focus on that. So we have these two symbols, one to turn our eyes towards a group of numbers that have a characteristic, and a different symbol to point us in the direction of a single interesting number and its interesting characteristic. So the symbol for the single interesting number is this backwards E. So when we see this symbol, we actually say this phrase: there exists. There exists. And I'm going to put in parentheses here, at least one. So there exists at least one. And here's an example of what I mean. There exists a real number, we're just calling it x. There exists a real number such that 1 divided by that number is not a real number. So let me read that again. There exists at least one real number such that 1 over that number is not a real number. So this is a declarative statement, and it is actually true. And if you think for a few seconds, you'll probably find that it's true, because if you take any number and you divide by 0, that's undefined. It's not a real number. So if I do that with the magic number 0 being x, I get something that's not real. So that's true. The second symbol is this upside down A, and we read that as for every, which means that whatever's going to come after this symbol is true for every number in this group that I'm going to choose. So here, for every natural, so I'm choosing the group of naturals, for every natural number, the square of that number is also a natural number. Is that true? Yes, it is definitely true. If I take any natural number and I square it, the result is going to be another natural number. There's no way to get other than a natural number if I square it. Okay, a couple more examples. So here, I wrote x comma y after the for every. That means I'm talking about a pair of numbers. So whatever I'm going to say next is true or possibly false for a pair of numbers. So for every pair of real numbers, x plus y equals y plus x. Take any pair of numbers, add them up. If you switch the order, do you get the same result? Yes, this is true. You might recognize this as the commutative property. Properties are always true for real numbers. So if you know the commutative property, you already knew that was true. Here's another one. I'm using there exists at least one. There exists a pair of natural numbers this time. So there exists a pair of natural numbers such that the product, x times y, equals y. So the product of those two numbers equals the second number. So does that exist? Does a pair like that exist? And yes, that is also true because I could make x equal 1, right? If I make x equal 1, then it doesn't matter what natural number y is. Any natural number will do. You will get a product of y because 1 times anything is itself. Now you might be wondering, well, when all these examples are true, can you give me one that's false? Okay, here's one that's false. It's a variation of this one here, the commutative property one. Here's one that's false. For every pair of real numbers, x minus y equals y minus x. No. If you take two real numbers and subtract them and then switch the order, you're not necessarily going to get the same result. 5 minus 4 is not the same as 4 minus 5. It works sometimes. If x equals y, then I'm going to get 0 on both sides no matter what order I subtract the two numbers, right? Or if both of them are 0, I'll get 0 on both sides also. But since I said for every, it can only be true if it's true in every case. That's what for every means. Every case. If you find even one case, one example where it doesn't work, then you must say false. Here we have many cases where it wouldn't work, but it only takes one case for you to say no, that's wrong, false. Okay, now we get a little more complicated. By combining both there exists and for every in the same statement. So I'm just going to call these combos, quantifier combos. Okay, so it's got three sections here. For every real number, there exists a real number such that their sum is 0. For every real number, there exists a real number such that their sum is 0. So first of all, what am I actually claiming? By starting the phrase or sentence with for every, I'm saying that for every real number, which I will call x1, x2, x3, x4, every real number in the universe, I can find a y, but not necessarily the same y for every x, any y, any real number, such that the sum is always 0. That's what this is claiming. Pick any real, I can find a real to add to it to make 0. So it shouldn't take too long to think that, come to the conclusion that this is true. If I pick any real number, let's say 5, I can add the inverse of it, the additive inverse of it, to make 0. If I start with a negative number, I can add the inverse again to make 0. It works with fractions too. It works with irrationals. And if I start with 0, I just add 0 to it to get 0. So I can always find a partner to go with it to make 0. So this is true. Now, if I switch it around by starting with there exists, the statement is saying something very different. So don't think of all these real numbers here and then a partner to go with each of them. This is not what this statement is saying. There exists a whole number such that for every real, x plus y equals y. This is what I'm claiming. That there exists a whole number is a single unique x such that if I interact that x with all the y's, y1, y2, y3, y4, y5, y6, etc., and I add them, add the x to every one of these y's, I will get that same y back. That's the claim. Is there a magic number x such that if I add it to any real number, it doesn't change the real number? And the answer is yes. There is a magic number that performs like that. 0, right? If x is 0, then that happens all the time. In fact, I even wrote a big 0 around that x. I gave you the answer. All right, so compare these two diagrams. These are different, saying different things. Start with for every, followed by there exists, means this. Start with there exists, followed by for every, means that there's a magic whole number x here that interacts with all the y's to do this. Okay, make sure you don't get confused with those two. Okay, so that's quantifiers, and we'll see you in class later. Bye-bye.